the remaining topics from chapter 15. Yep, chapter 15. It's a sort of it's a bit of a hodgepodge, but we were trying to organize things that made sense, and we had a little bit of extra stuff on the end. So here we are. I'm going to start by talking about some issues and some technology and some ideas related to what we've been talking about, which are the yesterday, or was it yesterday? Yeah, it was yesterday for you guys. This little lab work yesterday, an acid deposition. We looked at how rocks neutralized the acid, but the granite didn't, which is significant because the soils, for example, in this part of the country tend to have more limestone in them. There's limestone bedrock, and they can buffer acids better than the granite-based soils in the Northeast. So we'll talk a little bit today about how to reduce those types of pollutants and what's done and what's been successful in that regard. Then we'll transition to another topic altogether, which is ozone depletion. Not to be confused with ozone, the air pollutant down here that's an irritant and damaging to plant tissue and stuff, but rather ozone way up in the stratosphere, a different topic altogether. So we'll talk about that. And then the last thing is indoor air pollution, not something that's often thought of as an air pollution type. It's not the first thing we think of anyway when we think about air pollution. It's a significant issue nonetheless, so we'll talk about that as well. Nope, Monday. We will have another lab day. In that class, we're going to be thinking of the chemistry that I showed today, as well as some of the chemistry we talked about yesterday with the acids forming in the atmosphere and such. Because in this particular unit, and not so much that you need to be able to explain chemical reactions, but map them out and model them. So we'll spend some time with that. The other thing for tomorrow is we will go back and hopefully find all of our little slides with the tape on it that we put out to. We'll examine that to look for particulate and sort of characterize what we see a little bit. That's our sort of our short-term outlook. Next week we'll get into climate change and the last big topic, and we'll have our assessment. We'll be on our way. Questions about any of that? Still? Okay. So I thought I'd start with this. A big topic yesterday was this idea the impact of the pollution, of air pollution, can be and are felt at times great distances from where the pollution originated. It's because air pollutants travel with the wind, right? They're in the atmosphere, they're going to travel with the wind. So this, first of all, this little graphic here, this is from the reading you were given yesterday, the Hubbard-Brooke assessment of the effects of acid rain. And what you're seeing are these bars here represent the amount up here on the top of sulfur dioxide being produced in these places. The black bar shows, let's see, what's the black bar? The black bar is showing like the early 90s, the yellow bar is showing the mid to late 90s. Down here we have nitrogen oxides, same thing. We're seeing how much is produced in these different places. The beginning of the 90s and in the late 90s. The map over here is showing us the direction that pollutants tend to move from sources to wherever they end up. And what you should, so the way you read this is the wind moves in the direction of the tapered end. Okay. So the we saw yesterday, the pollutants from the Midwest and the kind of the Great Lakes region end up moving north and east over New England and eastern Canada. You can see some other examples from around the world. We do see there is evidence of pollution from China making it to the Pacific Northwest, for example. That's been documented. It's been measured. We, for example, they It wasn't too long ago, there's an article published about how radiation from the nuclear reactor meltdown in Japan a few years back related to the tsunami and earthquake that happened there, radiation from that ended up here in the Pacific Northwest as well. They could actually measurable amounts show up. So great distances, right? The impacts might be felt very far from where the source was. I should point out, too, before I move on, notice the different, so at the top, this is sulfur dioxide up here. There's a few places that have really big bars: Ohio, Indiana, Illinois, Pennsylvania. Missouri did pretty good. But there's a lot more places that have big bars of the nitrogen oxides. Why might that be, do you think? Think of the source of these things. What do we associate sulfur dioxide with? Burning coal, right? Coal power plants is like the big thing. What do we associate nitrogen oxides with? Mostly. What? It's not coal. Cars, automobiles, right? Things like that. Knowing that, maybe it's not surprising that we see a lot more bigger bars down here, right? There are a lot more places producing a lot of nitrogen oxide than sulfur dioxide. Just kind of an interesting observation, I thought. You'll notice also here, if you check out the color codes, let's see. So this kind of brownish color are areas with significant atmospheric pollution. So the air's dirty, right? But where's the acid rain falling? Well, it's falling here, right? We have primary pollutants being formed, secondary pollutants in the atmosphere being deposited somewhere else. Okay. So, anyway, air pollution travels, right? So, how do we deal with the pollution? What do we do about it? Well, what we do about it is we reduce it at the source. Okay, fairly obvious. But once it's in the air, it's going to be much more difficult to deal with than at the source. So that's what we do. And so, for example, this is from your book here. This is a diagram of what's called a scrubber. And what a scrubber does is it removes particulate, it removes sulfur oxides and nitrogen oxides from exhaust emissions. And it does that by bathing the emissions in water. In other cases, things like electrostatic filters, which kind of electrically attract particulate. Different ways to, the different technologies exist to accomplish similar things. But this scrubber technology is kind of the classic example. And so we prevent it from ever leaving the factory or from leaving the power plant. That's the idea. Okay. You end up with, much like we've seen before, a waste product that needs to be disposed of. But at least it's a waste product that's right here that I have control over. It's not a waste product up there going wherever the wind goes. Okay. So this scrubber thing is a big deal. You're going to want to be somewhat familiar with that technology. It's broken out here in some pretty basic terms. Being asked about chemical, it's just the basic steps in the process. Another sort of similar but different example is shown down here. Catalytic converters. These are on cars, if you've ever looked under a car or not, but it's a part of the exhaust, the car exhaust. So before the tailpipe exhaust comes out, you've got this thing called the catalytic converter. And what that does is it captures the nitrogen oxides that would otherwise be in the environment. Things like this, technologies like that, have proven to be very effective at removing a lot of pollutants at the source. It's of sort of universal adoption in some cases. Like, are we going to see even more improvement or not? The catalytic converter thing is interesting. In some parts of the country, for example, California, where they have really intense air pollution concerns compared to some other places, there's all kinds of rules about selling a car without replace your converter before you sell a car often. From experience, when I bought a car out there, I had to spend a few $100s getting a new catalytic converter on it so it would pass inspection so the guy could sell it, for example. Also, you can put more than one. And then there was talk of that, too, in certain cars, certain types of vehicles that are big emitters, more than one catalytic converter. Other things that we can do, less related to technology and more related to like behaviors or like policy regulation kind of thing. This is an interesting one. Controlling the temperature. If you burn something really hot, fuel of any kind, if you burn it really hot, it's kind of a less orderly reaction, right? You end up with a less complete reaction, a less complete combustion, which makes it a little counterintuitive. Like, it's really hot. Well, not really. It's a chaotic place, right? There's a lot of disorder in that system, and some of these pollutants escape. So if you turn it down, you do more controlled burn, you ensure you burn up more completely, and therefore reduce the amount of primary pollutants during the environment. Yeah. Another one is very much related to policy and behavior. This idea that depending on where we are, we can governments can decide to limit days of driving. Mexico City was an example in the book. Depending on your license plate number, or even you can drive on odd or even days. Okay. Carpool lanes, establishing increasing the cost of driving, tolls and such, toll roads, cost for parking. Different ways to incentivize to or drive less. Can be effective. VOCs. These are the ingredient, along with the nitric oxides. They're the ingredients. Yeah, right. It's like, materials, chemicals, are VOCs. Things like, and these kind of industrial solvents are VOCs. So if these are issues in certain places, industrial centers or what have you, local governments will choose to regulate them. You see a good example was discussed the other day when Mr. Zay lectured, talking about temperature inversions in Colorado. There are different rules about creating emissions in these places are a problem compared to others. So it's true here with these and accents. The other thing we can do, I mentioned incentivize to create incentives not to drink. Well, this is kind of on a bigger scale, kind of a more like at the more industrial level. Incentivize or create incentives to. And one of the things that the Clean Air Act of 1990 has been brought up a few times. It's related very much to the stuff we studied or looked at yesterday in the lab. Big things that came from that and the amendments followed was this idea of cap and trade. Excuse me. What this is, it's what we call a market-based solution. Market-based solutions are different than regulations that create penalties. So it's easy to say, well, if you do this or do that, there are going to be penalties. Pay your fine. That's one way to do it. We can all think of examples of that in our lives, speeding tickets and such. And nobody wants to be penalized and lose money in that way, right? But when it comes to business and industry, and when we're talking about the electricity or essential services that everybody kind of wants and needs, it's kind of a tough argument to make to the manufacturers, for example, that you're now going to be penalized for creating pollution, right? We all want what you're making, but we're going to penalize you for polluting also. That doesn't go over well, right? Maybe there's an argument to be had there, for sure, but the more palatable argument is this market-based. So what this means is the way it works is we create a cap, meaning we establish a an amount of pollution that we're going to say is the total amount that is allowed. This is how much we think is okay. So total. Then we go and we look and we say, all right, these are all of our polluters. Okay? And so that now everybody gets a piece of the pie. Okay? You're allowed this much total. You've got this many businesses, so everybody gets a little piece. That's your allotment. The market, we call it market-based solution because if you don't use your entire allotment, you can sell what's left. So now you have your incentive to not pollute is the fact that you can make money off of not polluting. Right? I can sell my credits to some other industry or business of some kind that is a big polluter and is going to have a hard time. Like if costs are really high for these people over here to reduce their emissions for whatever reason, they're not going to want to do that. But if I don't need all of my allotments and I sell them some of it, well then they can pollute a little more because I'm not. And I get the money. And that's a good thing. They save money. It should work out that they save money by not having to change their whole production and start technology. Okay, so this kind of market-based thing, you might hear that term. It's a similar thing with we're talking about climate change. People want to hear about market-based solutions because that seems to motivate more than, in some cases, penalties. I do want to point out this little diagram I found here, which is all over the internet, by the way, if you're Googling it. Carbon dioxide is the example. I just want to make clear that carbon dioxide is not part of this Air Act in 1991. Okay? Carbon dioxide was not recognized as a pollutant until 2014. That was only after the courts got involved and said, yeah, no, the EPA can regulate carbon dioxide. And this had a lot to do with the fact that climate change wasn't so widely accepted in a variety of reasons. But what was included in the Clean Air Act of 1990 were the nitrogen salts. Okay? And the same idea was applied to that. If you're a coal power plant burning coal that contains a lot of sulfur, then you have a certain amount of sulfur you can emit, and otherwise you have to stop emitting or buy credits to allow you. Questions about that? This is like in the grand scheme of the course, it's not like a huge thing, but it's kind of one of those key ideas that when you're asked about what to do about something, whatever the issue is, how to stop pollution, how to preserve biodiversity or whatever, this idea of a market-based approach is a very popular one. Okay, we're going to transition here. New topic. Ozone. Before that, though, I want to bring you back to Earth's travel theme here because I want to point something out. We saw an example of how Earth would travel like on air currents sort of regionally, or maybe across the continent. It's also true that air pollutants will travel on convection currents from the equator to the poles. No offense. They will travel on convection currents from the equator to the poles. Why from the equator to the poles? Because the equator is the high energy place. They always go from high to low, right? Remember that? Big deal. Big deal. I want something else. From high to low. All right, a lot of evaporation around the equator, in the tropics, pushing gases away from it. Pollutants are going to travel that way too. Turns out, the more volatile the chemical, the farther it can travel. Assuming it will persist and not chemically break down along the way, we tend to see these highly volatile chemicals get sort of concentrated at the pole. So, that in mind as we go forward. Ozone. Ozone's been a bad character up until right now. Ozone's a bad thing because ozone contributes to the formation of smog. And it's an eye irritant, a lung irritant. It makes people sick. Well, that ozone that we've been talking about, the ozone that damages leaves on trees and stuff, is ozone down here in the troposphere, or rubus, ground level ozone. Okay? That's bad ozone. Ozone, by the way, is O3. Okay, good ozone is up in the stratosphere. Same molecule, different place. Okay? Up there, it does an incredibly important job. It absorbs ultraviolet radiation. It absorbs ultraviolet radiation that would otherwise damage tissues, plants, and ecosystems in a major way. These are pretty high energy wavelengths, and they are damaging. You get sunburn, for example, from ultraviolet. And that's good ozone. So how do we end up with ozone up there? What is the deal? Why is it there? Well, it's shown here. What's happening is this. Oxygen, O2, from down here, makes its way up. Upon getting up there, it's exposed to ultraviolet. Notice the numbers here. These are smaller numbers than those numbers. Shorter wavelengths, higher wavelengths. So this is shorter wavelengths is higher energy. Okay? So these higher energy wavelengths, this ultraviolet, breaks apart oxygen molecules. And then these free oxygens combine with an oxygen molecule to form O3, ozone. And now we have an ozone layer. Right? Oxygen is going up there and getting chemically changed by this radiation into something else. O3. So there's some UV light being absorbed in the ozone layer. So this can convert to O2. What's also happening is some lower energy UV lights, some slightly longer wavelengths, are hitting O3 molecules up there, breaking them apart into oxygen and O2. Well, oxygen, a free oxygen plus O2, that's the recipe for ozone. So we go back and forth. Okay? The whole while, ultraviolet lights hitting these molecules, changing some of them to O3, changing O3 back to O2, that O2 back to O3, and around we go. Okay? We have an ozone layer shielding us from ultraviolet light in this way. So that ultraviolet light is helping these molecules and these organisms. That's a good thing. That keeps us alive. It keeps Earth the way we know it and the way we love it. What's also interesting to know about this is where's the oxygen come from? Well, the oxygen comes from plants doing photosynthesis. So there was no ozone there before the plants started photosynthesis. So the plants, which are the base of our food web, and provide energy to everything above them in that pyramid. While doing that, they're also contributing the chemical that ends up in the atmosphere and creates the ozone layer, which allows life to survive as we know. This is really nice imagery. The ozone layer formed, many millions of years ago, billions of years ago, once photosynthesis started putting oxygen in the atmosphere in large amounts. So we've got the ozone layer. And that's good. Turns out that in the 70s, the early-ish 70s, researchers started to notice that over Antarctica, for part of the year, the ozone layer was basically cut in half. The amount of ozone in the stratosphere was drastically reduced for part of the year. And what they figured out, and this won them the Nobel Prize, by the way, they figured out that this was happening because of pollution. Chemicals, these volatile organic compounds, that contain chlorine, bromine, fluorine, iodine, halogens, really reactive elements, group 17 element. Here are those chemicals are ending up in the Antarctic and reacting with ozone to turn it back into oxygen. So I just showed you how to go back and forth, right? But with the addition of these chemicals, things are being tilted towards the O2. We're getting less O3 and more O2 because of the presence of these chemicals. Now, I'll talk about the chemistry in a second, but first this. Which months and why? Cool. What season is it? Okay, maybe I'll just. I'm curious. What season is it in Antarctica right now? It's fall. What season is it here? Spring. Nice. Okay. So this is showing you September. So what season is it in Antarctica in September? Spring. Right? It's fall here. It's spring there. So which months? It's the spring and the summer months. Why?
Because in the winter there's a lot of, I think, is it chlorine?
Chlorine is one player.
Yeah, it gets built up in the ice, I believe, and then in the early spring, because there's more heat, it starts to melt, and then that.
Okay, so the thing about more heat.
Yeah.
Let's think about that for a second. Why is there more heat suddenly? Because it's spring. Think about the tilt of the Earth that's happening to Antarctica. Where's it been? During its winter, it's been tilted. The sun's over there. It's been tilted away from the sun, right? During the spring, it's being tilted back towards the sun. So it's hotter because there's more sunlight, right? Antarctica was mostly in the dark for all of its winter. Okay? But here in the spring and the summer, it's starting to get bathed in more sunlight, and therefore in more ultraviolet. So the whole time that chemicals have been moving around during the winter and accumulating and stuff, they've just been kind of sitting. But then you keep moving around the sun, and the southern part of the Earth starts tilting towards the sun because it's entering their spring and their summer, and those chemicals are now exposed to the ultraviolet light that's going to start doing the work of breaking all these ozone molecules. Now, a lot of words on there. Don't copy them down. We're going to give the slides are available to you after class. We're going to tomorrow spend some time thinking about molecules. We'll have some diagrams, all that stuff. Will be when you take record time. But let's talk about it for a second. Our pollutants, our category of pollutants are these CFCs, chlorofluorocarbons. Volatile organic compounds, right? Volatile because they got that chlorine and fluorine in there, really reactive stuff. Organic because they're carbon-based molecules. They make their way to the Antarctic, they get hit by UV light, and they break apart. And now we've got these free chlorine atoms, chlorine ions, free fluorine ions. Sometimes these are called radicals in this setting. And what they do is they start also really reactive. So ozone is really reactive stuff. That's why it's an irritant. It's reactive. Well, it and chlorine react together. That's what reactive things do. And what that means is chlorine is picking off an oxygen and converting it back to O2. Okay? That O2 doesn't do the same thing as O3, right? You're shifting it, like I said, towards the O2. You're taking away O3 and then you have no. But notice this, right? I picked that oxygen off and I created an O2 molecule. Well, that chlorine loses that free oxygen, and now it's creating again, and it can do the same thing, right? So the chlorine doesn't break down. Chlorine's not consumed into some chemical compound that stops the process. a single chlorine atom can break down many ozone molecules for that reason. Translation, it doesn't take a lot of these things to break down a lot of ozone. Okay. I neglected to mention where these things come from. CFCs, they are uniquely human. Right? They are not found in nature, naturally from it. They are anthropogenic, these things. They were used in coolants, things like refrigerants, the cooling liquids that were in refrigerators, in car radiators, things like that. They were also propellants in aerosol cans, like old school hairspray cans, things like that. They added these chemicals to help propel and create the mist. Really commonly used substances for a long time. And that's where they came. Okay. Since then, having figured out this whole their presence in the environment has been reduced. I'll talk about that in a second. I'm getting a little bit ahead. I have one more question before we get to that. Why Antarctica? When they first noticed this, it was just Antarctica, not the Arctic. I'll show you this picture now. Since then, after it was identified in the Antarctic, a similar hole in the ozone was noticed in the Arctic during summer, spring and summer, in the northern hemisphere. But it took longer to notice that one. It wasn't as prevalent. Same thing happens. The tilt changes, right? The Arctic spends most of its winter in the dark, and in the spring it tilts back towards the sun, or UV light's back, and you get chemical changes happening. So why Antarctica? Why did they see it in Antarctica? Why do you suppose that? This is pretty clear. How was the ice? What else is there more of? Ocean, right? Wind. Sorry. Yeah, what's this right here?
The west wind.
It's the west wind drift. That's an ocean current being pushed by wind. Westerly winds. So, what now? This is the part that stick with me here. The Earth is round, right? So at the bottom of the Earth, of this sphere, we have Antarctica, and around Antarctica, we have this current, this wind and ocean current, that is not present up here. Well, land up there, getting in the way. So yeah, this current here, this west wind drift, kind of isolates things. And once they get there in Antarctica, they're kind of trapped, and by the current. Okay. So we've got this movement happening away from the equator. Things are being deposited at the poles, and now in the southern part of the Earth, we've got these currents kind of trapped. Okay. When Earth tilts, the Antarctica is back in the sun. Those trapped pollutants are now reacting the way it is. So back to the conversation about what we did about it. What we did about it was many places. Did about 24 countries, I think it was 24. They signed the Montreal Protocol. This was an agreement made internationally to ban the use and in some parts, ban the use of CFCs, these chemicals, in places like the United States and some more highly developed places, and to phase them out in others. Remove them from the environment. Use something else. Find an alternative. And that's what was done. Okay, so a lot of nations agreed, okay, let's do this. We don't have the whole ozone layer, it's not good for any of us. We know exactly what the problem is. This is the solvable problem. let's do it. So they did. And it is projected, the ozone layer is projected, to recover back to its, what we would call normal levels by the end of the century. It's on the upswing, has been for a little while. It's certainly not declining anymore. And it's the result of this cooperation, it's the result of this sort of will to do something. So good news. An example of how regulation, how agreement policy can lead to positive outcomes. Questions on that? Too far ahead. Okay. So that's let's see. Yeah, that's the deal with ozone. These questions of why Antarctica, why the spring and summer, those are important ones. As is this, the formation of ozone and how ozone layer maintains. We'll circle back to some of that stuff on Monday when we get into it. All right, last thing. Excuse me. Indoor air pollution. Like I was saying, not the thing that people tend to think of first when they think about air pollution, but still a significant issue. You can see right here that in bold one of the main ideas. This is, in the developing world, a very different issue than in the developed world. But there's stuff to talk about on both sides. And 90% of the deaths attributed to indoor air pollution occur in developing countries because what we're talking about here is the burning of materials like coal, like manure, like plant matter, like indoors, to heat and to cook. Okay? This is everyday life for a large part of the world, which means everyday exposure to particulate, to carbon monoxide, to chemicals found in those things that can be used. Which is why it's a very big deal when people go to these parts of the world with things like solar cookers or gas stoves, things that don't require them to burn coal indoors, to burn wood, such as something we'll talk a little bit about when we talk about climate change. So anyway, right, a different issue here. In the developed world, it's more about exposure to chemicals that are in building materials and household goods related to everyday life in the developed world. There is this term that is sick building syndrome. It's been given a name because it's very noticeable. In modern buildings, which are really tightly wrapped, highly insulated, closed-off places from the environment, from the external environment. In that setting, you create a situation where you're going to be exposed to higher concentrations of these things. Okay? If your house is really drafty, maybe it doesn't have insulation in the walls, like older homes, for example, then this might not be the same issue as it would be in a newer building, kind of an unexpected outcome. But the kind of stuff we're talking about, you can see illustrated in the diagram here. Things like furniture, foam insulation, pressure-treated wood, all contain really volatile organic compounds. Things that slowly over time make their way into the air, into your clothing, and things like that. Also at issue are things like household products, paints, paint thinner, cleaning products, things like that. So if you think about who's at the greatest risk for these due to from exposure to these things, you think about kids, okay, because their systems are young, they're developing. You think about the elderly, because the systems are old and in decline. You think about people like the people building the homes. You think about people cleaning the homes. Right? People that are exposed to these chemicals much more closely. Asbestos and radon are two other ones that are important to know about. They're described in the book in some more detail. But asbestos is something that you find more in older homes and newer homes, older buildings. It's a carcinogen, as is radon. Radon will result in radioactive decay of minerals in the soil. Okay, I'm done. You go.
They all were like, they all just factory workers like they were breathing it in. I think why? You don't do that. That is awful. 75% of more than 35
Oh my gosh, that video. I do not like that.